Dear viewers, I have decided to make a little video on some research I did on a couple of different gunpowders for my 6.5 Creedmoor. I think I want to start with a little bit of warning. Unless you are reloading your own ammunition and you're really into precision of your rifle, this video is probably not for you. It's going to be a little nerdy, I will admit that. But I think it's interesting, so for those of you that might find it interesting, here we go. A little bit of background. I've been shooting my Sarco S20 Precision for, I don't know, 3-4 years now, and I initially created a load which has served me really well. It has been really satisfied with the precision of that load. It's based on Vithavuori N555, and yeah, I've been shooting it on several occasions. You can find some videos on my channel, including in Norway, where we're shooting out to about 1,030 meters. So over all these shooting sessions, I've noticed multiple times that it's really on target out until 900 meters. There's a big difference between 900 meters and 1,030, which is the target we're typically shooting. I'm starting to have misses where I don't really expect to have misses. And so I guess after looking into it, it kind of became obvious that the reason for that is that the projectile is hitting transonic range. And that's kind of, that's a problem. Anything transonic is not good for projectile flight. So I got the idea that maybe I should try to load with some different powder to see if I could increase muzzle velocity to being able to consistently hit at the 1,030 meter target, or just a kilometer. So here we go. What I did was, I think I'll just go into the analysis, and you can take a look here at my website. So if you go to research.baso.dk, you can find under analysis, there's the latest at this point is this particular analysis, and I will walk through the essential parts of it and try to kind of give you my conclusion on this. So the questions that I asked myself were how does precision compare, meaning on the target? How does muzzle velocity compare? And how does muzzle velocity consistency compare? Which, as you will see, becomes quite important. And how does muzzle velocity temperature dependency compare to the Vithavuori N555? And how is the effective range, meaning supersonic range, not transonic range, how is that affected? So the way that I did this, and I'll just scroll down a little bit here, you can see my rifle, by the way, and the conditions under which I shot. The way I did it was, and here also the loads, by the way. The way I did it was, the whole thing came in kind of 3 phases, if you will. First, I made 4 sets of 3 rounds of ammunition with the URP, Norma URP based, which is the one I'm testing against. And I put, the day before, I put 1 set in the freezer, 1 in ice water, and 1 in just room temperature, and 1 in hot water. I did that in the morning. And then I shot, I used a chronograph, of course. I shot these 3 sets of rounds and measured the muzzle velocity. And the idea, of course, is to find out the dependency or the variation with powder temperature. I wanted to compare that to the Vithavuori N555. And then the second round was to take just for comparison, to make sure that everything was fair. I took 10 rounds of the ammunition I've been shooting for years. I put 10 shots on a paper target, and then I did lastly 10 shots with this new candidate, the Norma URP based ammunition. And I also want to say that I was shooting at 200 meters. So what I found was this. I looked into the muzzle velocity versus temperature, and I'll show you a diagram in a bit, but it came out like this. So the difference between minus 12 degrees and 38 is 20 to 23 meters per second, a difference. And here are the targets. The first one you have on top here is for the old load, so to speak, the Vithavuori N555. And the second one is for the Norma URP. It looks like, just eyeballing, that maybe the Norma URP based is a better group. You might argue, but really I tend to look at these things from a statistical perspective. So I keyed them into my target analysis software, and what I found was that the D5X, which is really the expected 5-shot group size statistically, is 0.78 MOA for the old loads, for the 6.5 load, which is respectable enough. I mean, most people talk about subsonic as, sub-MOA as being good, so this is certainly sub-MOA. And the European load came out as 0.5 MOA, so it's a nice group. It's a nice little group at 200 meters. But the fact of the matter is that due to the very limited number of shots in these strings, the confidence interval, meaning the to what degree can you actually trust these D5Xs, is so large because of the small number that there's a huge overlap, and really statistically speaking, there's not evidence to suggest that these group sizes are statistically different. So the conclusion really is that there's the precision, at least at 200 meters, is not different. We cannot say that. So that's fine, but that's on 200 meters. And here are the confidence intervals and all of that. Then the next interesting question is, sorry, I'm getting a little bit ahead of myself here. This table you have here is the average or mean muzzle velocities for the two loads. The SSA is the Vithavuori load, and the SSA-X is a Norma load. And as you can see, as we kind of already saw, the muzzle velocity average of the Norma load is 810, whereas the average velocity of the Norma load is 780. So 30 meters per second-ish more muzzle velocity on average. But here's a really interesting thing. The standard deviation, meaning the spread or the variation of the muzzle velocity, is different. Without making this a stat lesson, I will just say this. I assume that the muzzle velocities follow a normal distribution, and now we got the standard deviation, and then you can relatively easy determine the 95% confidence interval, or the 95% interval of the shots by taking average minus 2 standard deviations to average plus 2 standard deviation. That interval, you will expect 95% of the shots to fall within that interval. So, long story short, the Vithavuori load, we expect 95% of the shots to fall within 777 meters per second up to 783. And for the Norma-based load, the interval is larger because the standard deviation is larger. So it's from 803 to 818-ish. So then my thinking was, okay, so I took my ballistic solver, my applied ballistics, which has proven to be very, very reliable, especially when I use custom drag models. I kind of do cold bore shots and hit most of the time, so I trust that a lot. So the question becomes, what's the effect of the spread or the variance in muzzle velocity on the vertical dispersion on the target at different distances? So the idea is to take the slowest muzzle velocity and the fastest muzzle velocity for load, and then determine the solution for the ballistic solver. And then when we have the solutions, we can calculate the vertical distance difference between the slowest shot and the fastest shot within this 95% interval. So the point is what you see here. On 200 meters, the difference or dispersion, the vertical dispersion from the Vithavuori load is 0.2 centimeters, so like 2 millimeters. And for the normal load, it's 0.6 centimeters, so 6 millimeters. So really, and this was the distance I was shooting, it's kind of, it's not significant. It's very, very small dispersion based on the muzzle velocity. So then I continued the exercise for different target distances, and you can see that for on 400 meters, it's 1.6 centimeters and 4 centimeters, which is also not huge difference. But then we get to 600 meters, it becomes like 4.8 and 12.6. So now we're beginning to see like a more significant realistic difference on the target, and all the way down to on 1 kilometer, the vertical dispersion for the Vithavuori load is 20 centimeters, whereas 53 for the normal load. Keep in mind, this dispersion has only to do with the variation in muzzle velocity. Of course, in real life there are other factors, but I want to isolate the effect of muzzle velocity variation. So, since the standard deviation is about 2.7 times larger, this actually means that the confidence interval for the vertical dispersion is approximately the same, 2.6. And so and this is of course a personal preference, but I will say for hunting application out to say 300 meters, which would be a really long shot for me anyways, I wouldn't hunt on that distance, at least not the first shot, maybe a follow-up. Then this dispersion has no practical effect. So the normal load would be fine for hunting. But for long range shooting, like at a kilometer or something like this, I find that the 53 centimeter dispersion is something I don't want. So really, I will make one more point before I reach the conclusion, but I find that this dispersion is more than I want. Okay, then we have the effect of the powder temperature. You can see here that I have calculated the average muzzle velocities for different temperatures, and it's actually linear, almost linear. And if you calculate the gradient, it's 0.462 meters per second per degree centigrade for this Norma powder. I have from previous experiments the same number for the N555, which is 0.367, so slightly less. So then the question becomes, is this significant or not? And keep in mind, what I'm talking about here is I'm not suggesting that it's insignificant to consider powder temperature, because that's certainly very important, because as you can see, muzzle velocity varies. What I'm talking about is the difference between the two powders. So in order to try to understand that, I'm making the assumption that we have an error in the input temperature of 10 degrees centigrade, which could easily come from chambering around in a hot chamber and wait for just a few seconds and things will heat up and you might be off by quite a bit. So Anyways, I did the math. I looked up the velocities, and with a 10-degree error in input of powder temperature, the difference between the two gunpowders, or the error there, the difference is 0.95 meters per second. So for all practical purposes, I would argue that this difference is not significant. It's not to say that you should disregard powder temperature, but the difference between the powders is not significant. Okay, so last question, which is really, we should probably see together with the vertical dispersion, is what's the difference in effective range. So in order to estimate that, I make the assumption that effective range is out until the projectile drops to Mach 1.1 transonic range. After that, things start to go south for the projectile. So again, I used my ballistic solver, and what I find is that because it's the same projectile and everything, but because of the higher muzzle velocity of the Norma-based load, I reach Mach 1.1 60 meters longer downrange compared to the Vithavuori N555 load. So here we have it, and by the way, the effective range, meaning where I reach Mach 1.1, is around 1,000 meters, which is also what I found from my practical shooting. It of course depends on environment like air pressure and stuff like this. So anyways, this was the experiment. I will scroll up and I will give you my conclusion. I kind of went through all the findings here. They're just summarized up in the results section here. My conclusion is that for combined hunting and long range shooting up to a kilometer, which is what I'm doing, I still prefer Vithavuori N555. And that is, of course, I mean, had the muzzle velocity variation have been not so different, of course I would have preferred the higher muzzle velocity and get more effective range, but to my taste, the increase in vertical dispersion based on muzzle velocity variation is I mean the additional effective range do not make up for that additional variation to the shot. So anyways, I realize it's a bit nerdy, but I know there are reloaders out there that might find this interesting, so maybe I saved you some time and money, and if you have any input, any questions, feel free to contact me. Thanks for watching.